Hello everybody, my name is Zoltán Miragy. I am a structural engineer, a CEO of Lapidarium Engineering Ltd. And I would like to present this recording of my presentation at CESBP conference held at Budapest, Hungary on 11th of September. And this presentation was about the research work we have done together with Zsuzsa Szalay. And the topic was the low carbon possibilities on residential building design. When we talk about embodied carbon, the discussion often starts with great global values, numbers, or great percentages. What is less discussed is the enormous variation that exists in a certain design, a certain building design for different technical variants. And looking at 906 technically feasible solution of a certain buildings, we have found a 60% difference between the best and the worst embodied carbon level. And this is an enormous difference. And what is striking news about it that these building variants, virtual building variants, weren't exotic or unrealistic design options. However, they were technically feasible solutions coming from European construction solutions. And this means that beside of looking at new materials, new technologies, we should also concentrate on the existing techniques and materials and find a way to better use them. So you cannot compare buildings with different geometries and different functions. It's very hard. Therefore, we created a homogeneous database of a certain building model. Here you can see this building was 7-story high and two basement story. And this simplified life cycle assessment analysis was only considering the A phase, the construction phase, so-called upfront carbon. This is a simplification. The carbon intensity of the different construction materials came from EPDs, environmental product declarations. We have aggregated from this database, and we didn't do any energy mix adjustments or allocation. We took these values as they were published, and we considered them as valid for European average. In order to create virtual buildings, first we have looked what type of building structural solutions exist in the market, and we have found these elements. You can see on the brackets the number of the types we have aggregated. So we basically collected substructure solutions, vertical, horizontal structure solutions, infill, both. And we designed them according to the same mechanical and thermal requirements. By this way, they can be each other's alternatives, and we can combine them for creating virtual building variants. These are the different frame solutions. Basically, we have columns and beam types of frames, and also we have wall type of frames. Few words about the low carbon design thinking. When you think of low carbon, you as an architect or as an engineer, you have three focus levels. The basic level is always the material level. That's where you try to find materials that has a low carbon intensity, and also avoid to use highly intensive materials. Then you create building structures. This is the combination of these materials, and you design them for certain regulations. That's where you can judge that for the same for the same purposes, what kind of assemblies are you using for walls? And the highest level of the low carbon thinking is when you have a combination of these building elements and you have a building, combined buildings. So when you design, you have to focus on these three levels at the same time because they interact with each other. And this three-level thinking, I think, is also valid not just for new construction, as for also valid for renovation and retrofitting. Let's see the results of an analysis. This is the 906 building variance. This is the distribution. What you can see here that the difference between the worst and the best cases is quite large, 60%. The worst embodied upfront carbon values belongs to buildings with concrete walls, and the best upfront carbon values belongs to timber frame buildings. It's a mistake on the slide. It says timber-based hybrid, not hybrid. This is solid timber frame. So what happens if you use, for example, green concrete? Okay, the concrete is, when you talk about embodied carbon, concrete is always the elephant in the room. I mean, you cannot avoid to deal with concrete because it is the most carbon intensive material. So what can you do to lower its embodied carbon level? For example, use less concrete. Also, you can lower the cement content of the concrete because the cement is the main part of the concrete carbon intensity. But if you lower the cement content, it has some certain mechanical limits. You just cannot use mechanical properties limit. You cannot use different concrete types for certain purposes. In cement production, 40% of the emission belongs to the chemical part, the carbon dioxide emission, and 60% belongs to the electrical part. It's quite large. And that's where you can use green energy. And this is also a very good way to reduce the carbon level of the concrete. And there are also cement factories that have carbon capture facility possibilities. This is also a promising way. What you can see here that by having the conservative assumption that we can lower by 40% the carbon level of the concrete, we have reached 24% shift in the lower median of the distribution. This is mainly due to that carbon sink of the basement. You know, the basement is concrete, is made of concrete for all the technical variants. So when you modify the carbon level of the concrete, you basically all the solution carbon level for all the solution shifts. What happens if you use green steel? For example, instead of using blast furnace technique, use electronic furnace techniques. That's where you can use green energy and lower emissions. And also you can use scrap steel. So as a conservative assumption, we have assumed 30% reduction in steel carbon level. But as you can see here, the difference is not high at all. I mean, we have experienced only 3 or 4% change in reduction. And this is even less for masonry. In this case, you can see only the middle part of the distribution moved. That's where we have reinforced concrete frames with infill walls, the masonry infill walls. This is an interesting slide here, that box diagram that is summarizes the carbon design range for certain frame types. On the left, you can see the timber frames that are the best versions, as long as the upfront carbon goes, as far as the upfront carbon goes. And on the right, you can see the green box diagram which belongs to the precast concrete. That's where you have to use cement 1, that is a very highly carbon intensive material, and it's overcompensate the smaller sizes of the precast frames. So you have a high carbon intensity for precast structures and also for RC wall frames. What is interesting for concrete lovers that the blue box, the range is quite high, quite large. I mean, when you use reinforced concrete, monolithic reinforced concrete, coupled with timber solutions, that is so-called hybrid systems, you can use CLT slabs with concrete tops, and you can use walls, timber walls or CLT walls. You can actually compete. You can challenge the pure timber solution. That is very good news, I think. Let's summarize our findings. As we have presented a novel approach in order to assess the upfront carbon level in early design phase for residential building, considering different technical solutions. In our research, we have found as much as 60% variation in the carbon design spectrum. That is quite large. Not a surprise, we have found that the concrete is the main driver as long as embodied carbon goes, and steel and masonry have limited influence on the carbon design. And also interesting news that the hybrid system can compete with pure timber solutions. In our future work, we should include other life cycle assessment phases, and also we should analyze different type of building structures and buildings with different functions. And in the end, I would say that when you think on low carbon design, concrete is always the main driver. Timber, where you can have savings, and structural design solutions, that all that matters. Thank you for watching. Bye bye.